Hi all, welcome to 12 applications. This is going to be our first bit of content that we're going to cover online. So the first topic we're doing is undirected graphs. It's chapter 5 in your textbook. This will be our last topic before we start exams. Some of you might have been in class for the first 1 or 2 bits. That's okay, we'll still cover it all anyway. I'll try and upload these on a weekly basis. Okay, and we'll probably cover 2 to 3 topics at the one time. It's my first time using this program, so bear with me if I'm a little bit slow doing a couple of things, and if some of my lines and stuff aren't very clean. Obviously I'll try and improve a bit as we get going. Okay, so let's get started. Okay, so basic concepts of graph. So what is a graph? Okay, so the vertices are the points on the graphs. Okay, so here, if you're looking at this graph here on our right hand of the screen, okay, you'll see that there are 6 vertices. Okay, the edges are the relationships, and they are the lines that join the vertices together. Okay, the degree of a vertex is the number of edges it has connected to it. Okay, so if we look at this blue vertex that's highlighted here, we can see it has 1, 2, 3 degrees. Okay, because it has 3 edges connected to it. Okay, so any graph with an edge that starts and finishes at the same vertex is a loop. So if we look down here, okay, because our edge starts and finishes at the same, this is known as a loop. If 2 vertices are connected, and 2 vertices are connected by an edge, and the vertices are said to be adjacent. Okay, so as you can see, vertice here adjacent, vertice and vertice adjacent, vertice and vertice are adjacent. Okay. If 2 or more edges connect the same 2 vertices, then the edges are said to be multiple edges. Okay, if they are directed, they must be in the same direction. Okay, for us, we're not really doing directed graphs in chapter 5, so direction is not too relevant, but we'll still mention it anyway for when we do it in semester 2 content. So if we look at vertice and vertice, okay, they have 2 edges that connect both of them, so these are known as multiple edges. Okay, so first example, here we have a network. Okay, it has 8 vertices. So if we go through and count the vertices, there are 8. There are 10 edges. Okay, there are 4 faces. What it means by the 4 faces, if we have, so this is 1 face, 2 face, 3 face, and the entire outside face is also, it's also a face, so that gives us 4 faces. Okay, here we have 6 vertices, 10 edges, and 6 faces. And here we have 5 vertices, 9 edges, and 6 faces. Okay, textbook questions for those, or that bit of content there is page 255 to 258, questions 1 to 9. I'm not going to make you do all the questions, but as long as you vary it up and do a couple of each, that should be fine for where after. Okay, so next bit is types of graphs. So the first one we'll look at is what we call a simple graph. So a simple graph contains no loops or multiple edges. Okay, so if we look here, we have no multiple edges, no loops. This here is a simple graph. Okay, next one we look at is a connected graph. Okay, it contains no isolated vertices, making each vertex reachable from each other vertex. Okay, so if we look at A and D, obviously they're not directly reachable, but they can be reached if we go A, C, D, or A, B, C, D. Okay, so there's still a path from each vertex to the other. Okay, what it means by no isolated vertex, so there's no vertex out here that doesn't have an edge connecting it to the rest of the graph. Okay, it's also not a split graph, so there's not 2 graphs next to each other. So yeah, that is a connected graph. A complete graph. Each vertex is connected to all the others. Okay, so if we look at this one here, okay, so if we're looking at this vertex here can reach every other vertex via an edge. So it hits here with that edge, that vertex with that edge, that one with that edge, and here with this edge. Okay, completed graphs probably aren't used that often. However, we still need to know what they are and kind of define them. So now we're looking at subgraph. So a subgraph is a graph that contains no vertices or edges that are not in the original graph. So here we're looking at G as being our original graph. Okay, so G is the original. G with a apostrophe is also is a subgraph of G, okay, because it contains the vertices, but not all the vertices, okay. However, it doesn't contain any new vertices, so all the vertices from the original, not all the vertices, but vertices from the original are contained on the subgraph, as are edges, okay. So there's nothing new, so it's essentially taking away stuff from the original graph while not adding anything extra, okay. So if we look at G with a double apostrophe, that is also a subgraph of G. Okay, next one we're looking at is directed graphs. Okay, can sometimes be called digraphs. Pretty much all it is your edges have an arrow which represents the way the network travels. Okay, so if we're looking at this one here, or this vertex here, okay, so this vertex can reach that vertex, but this vertex cannot reach that vertex. Okay, because it's suggesting that the travel or the directional arrow can only move one way. Okay. Bipartite graphs. A bipartite graph or bigraph is a graph whose vertices can be split into two distinct groups in such a way that each edge of the graph joins a vertex in the first group to a vertex in the second group. Okay, this will make more sense when we have a look at it, okay? So pretty much we're looking at our two subgroups. So in this case here, we're looking at the pink dots, or the solid pink dots with the white dots. Okay, so here you can see that the colored dots are their each group. So here, pink dot connects with both of our white dots, and same deal here. And the pink dots do not connect with each other. As soon as they start to connect with each other, it then does not become a bipartite graph. Okay, same deal here. So we have our solid pink dots versus our white dots. So our pink dots join up to all of our white dots. However, they do not join up with the pink dots. Same with the white dots. Okay, so you can see our two distinct groups we've used. Well, the two distinct groups are the two colors, so the pink and the white. Okay, so these are all examples of what we call a bipartite graph. Okay, these can be directional, but not always. So, types of graphs for your textbook questions, page 261 to 263, questions 1 to 10. Like I said, I don't expect you to do all the questions, but have a go at a few different ones, especially have a go at your reasoning and communication questions. Okay, so applications of graphs. So I'm going to run through some examples here. This is going to be a little bit hard for me to do with the drawing tool, but I'll give it a crack and see how we go. Okay, so I'm going to have a go at using the drawing tool here. Okay, so a meeting consists of two people that speak English, A and B, and three people that speak Chinese, C, D, and E, and one translator, I. Draw a network to show the list of communications. Okay, so like we covered in class, guys, it doesn't really... so everyone's is going to look different depending on how we kind of set out where our vertices are. Cool. So I'll try and set out A here, capitalize that A, B, C, D, D, E. Okay, and our translator is I. Okay. Sorry, just trying to look for my line tool. Okay, so we know that the people that speak English can obviously communicate with each other because they speak the same language. Okay, they can also both speak with our translator, who is I. Okay, the C, D, and E all speak Chinese, so they can communicate with each other. Okay, so that's what the edges are used to represent. So in this case, yeah, edges representing communication. Okay, so who can communicate with who? A and C cannot communicate with each other because they don't speak the same language. One speaks English, one speaks Chinese, but A and C can speak to each other through I, who is our interpreter, or our translator, sorry. Okay, as can D and I, and as can E and I. Okay, so this here is the network we're looking at. So it shows the lines of communication for essentially 6 people, 2 speaking English, 3 speaking Chinese, and 1 speaking both. Okay. We'll move on to our next example. Okay, I'm having another go with the drawing tool. I'm not too sure if you can see everything on the screen, but I'm just going to assume we can. So Troy being our last person on the list. Okay, so the weights of a judo club is shown in the table. Members are only allowed to compete against others within 10 kilos of their own weight. Draw a network showing which members can compete against each other. Okay, so same deal, guys. We still got to set up our vertices. We'll use letters to represent these. So Declan will use a D. Should be a little bit bigger. Matt will be an M. Warren, oh, I've forgotten Adam. Adam, it's going to be a very messy network in this case, guys. Obviously, once you've kind of done your draft, you can clean it up a bit if you need to. Keelan, Hoa, Leslie, Chris, Robbie, and Troy. Okay, I'm going to use the freehand draw line. That way I'm not intercepting other people's boxes. So it is going to be quite a messy one. So we'll start with Declan. So Declan is 82 kilos. So anyone within essentially 72 kilos and 92 kilos can compete against Declan. So that means I'll use a black line here. So Matt is able to compete against Declan. Okay, Adam is out of that weight range. He's too heavy. Warren is too light. Keelan is too light. Hoa is too light. Leslie is too light. Chris is within the weight range. Okay, and is Troy. Sorry, Robbie is too light, and so is Troy. So now we'll move on to Matt's weight. Okay, so Matt is 74 kilos, meaning he can compete against other people that are 84 kilos and 64 kilos. So Adam is too heavy for Matt. Warren is within his weight range. Keelan is within his weight range. Hoa is too light. Leslie is too light. Chris is too heavy. Robbie was within his weight range, and as is Troy. Okay, now we're going to move on to Adam. So Adam is 94 kilos, so he can compete against someone that is 84 kilos and 104 kilos. So Declan is too light, Matt is too light, Warren is too light, Keelan is too light. The only person he can compete against is Chris at this stage. So Adam and Chris have an edge. So we look at Warren. So Warren is 78 kilos to 58 kilos. Okay, so Declan is too heavy. Warren and Matt, they already have an edge there, so we don't need to represent that again. Adam is too heavy. Keelan is within range. Hoa is just outside range. Leslie is within Warren's range. Robbie is within range. And as is Troy. Okay, now we move on to Keelan. Okay, so Keelan is 71 kilos, meaning he can compete against people that are 81 and 61. Okay, so if you notice, because we've done everyone above Keelan, we don't actually need to address those people anymore. We only have to address the people below Keelan because we've gone in a set order. Okay, so Hoa is not within range. Leslie is within range. Chris is outside of range. Robbie is in range. And as is Troy. Let's run down the back all the way out here. Okay, now we look at Hoa. Hoa is 67 kilos to 47 kilos. The only person within range is Robbie and Leslie. So Robbie and Leslie. Okay, now we look at Leslie. Is 73 kilos to 53 kilos. Chris is too heavy. Leslie and Robbie. Go a little line on the outside there. And Troy is also within range. Okay, Chris is 96 to 76. Okay, so we set Robbie and Troy outside of his range. Then we go to Robbie. Robbie and Troy can compete against each other, and then we are finished. That is our network. Like I said, guys, it is quite messy. This will be something you need to look at in terms of tidying up. So it just depends how essentially you set your vertices out. Okay. Okay, so the textbook questions for applications and matrices are page 266 to 268, questions 1 to 9. Like I said, guys, do what you can. You don't have to do all of them. Okay? So next thing we're looking at, or our last topic for today, is adjacency matrix, or adjacency matrices. Okay, so we looked at this a little bit last year when we looked at matrices. Okay, so what it is a network will have a matrix which kind of shows the number theory behind the network. So if we're looking at this network here, it's an undirected network. So we have our vertices labeled, so 0 through to 4. Okay, so we set up as matrix as 0 through to 4, so from and to. Okay, so what we do is if a vertex can communicate with another vertex via an edge, okay, we put a 1 there. If it can't, we put a 0. So in this case here, can 0 communicate with 0? No, it can't, so we place a 0 in our matrix. Can 0 communicate with 1 directly? Yes, it can. So we put a 1 there because there is only one way 0 can communicate with 1. Okay, if there was, say, a multiple edge, then there'd be 2 ways it communicate, and we can put a 2 there. So if you look at the matrix here, you can see they're all 0s and 1s, meaning they're all one step, or each vertex can reach another one via one pathway, not 2 pathways. Okay, so now if we look at this one here as an example, difference being our vertices are labeled slightly differently. If we look here, we have a loop. So if we look at our D vertex, so D can get to D once via its own pathway, okay, which is what we call the loop. Okay, fairly easy. So in an undirected graph, each entry is a number of edges from vertex to vertex. The matrix is symmetrical, and a loop counts only as one edge. Okay, so we're not counting the loop going that way and back the other way. It only counts as 1. Okay, for a graph with n vertices, the adjacent matrix will be an n by n matrix. Okay, so in this case here we have 1, 2, 3, 4, 5 vertices. So our matrix then will be n times n, so 5 by 5 matrix. Obviously, if we had 8 vertices, it'd be 8 by 8. Okay, if we had 2 vertices, it would be a 2 by 2 matrix. Okay, as you notice here, guys, these are directed arrows, so it's a directed graph. In a directed graph, each entry is the number of directed edges from vertex to vertex. Okay, so if we look at 1 here, so from 1 we can reach 3, but from 3 we cannot reach 1. Okay, so we look at our matrix here. So from 1 to 3 there is one way of getting there. From 3 to 1 there is 0 ways because you can't go back up or the opposite way of the arrow or the direction. Okay, so if we look at 3 and 2, because those arrows go both ways, if we go from 3 to 2 there is 1, and if we go from 2 to 3 there is also 1. Okay, so what does the matrix essentially represent? So the first adjacency matrix gives a number of walks of 1 length. Okay, so how we can get to places via one pathway. Okay, the second, which is the square of the first matrix, so squaring the matrix, gives a number of 2-step length walks, or the number of 2 length walks. Okay, so in this case here, from V1 to V1, I can get to V1 using 2 paths once. So if I go I can do it twice. So if I go to V2 and back to V1, okay, that is a 2-edge or 2 relationship pathway. Same way I can go from V1 to V0 and back to V1 using 2 edges. I've used the same edge twice, but I'm still using 2 edges. And that's what the square of a matrix represents. It's the number of 2-step pathways that can occur within a matrix, within a network. Okay, that is the end for that, guys. I haven't put up the textbook questions yet. I will discuss those with you in our WebEx session or on Connect. If you have any questions, guys, feel free to email me through Connect, and I should be able to address those with you. Okay, thank you.